have to solve the problem by using the vector loop. And I have shown you how to draw it, how to derive the vector. And for you who felt that you didn't solve the problems, the questions by using the vector loop, so I hope in the next remedial next week, you can start learning from now, and then in the remedial test, you can solve the questions by using the vector loop. Okay, now I will start with the force, dynamic force of mechanisms. As I told you from the beginning, I wouldn't be long for today. I heard that you have other classes where you actually have to stare at the screen, the monitors. So I won't be long for today. I will give you a quick review first about dynamic force analysis of mechanisms. So the last topic that we are going to discuss, the title is dynamic force. Of mechanisms, of machinery or mechanisms, they're almost the same. Okay, dynamic forces of mechanisms. Because I have highlighted here dynamics, so you should understand what is the difference between dynamics and statics. Okay, the statics force analysis, you have done this probably in your second semester, I'm not sure. When I was a student, I have this class statics in the second semester. I'm not sure now. So this you have discussed this probably in your second or third semester. So what is the difference between the dynamics? In the statics analysis, you are using the first law of Newton, sigma F equal to 0. Why 0? Because there is no accelerations, or acceleration is very small, so that we can consider it is equal to 0. And here in the dynamics, we are using the second law of Newton. You remember in the rigid body analysis, there are three approaches, three methods to solve dynamic forces, which is the first one is by using second law of Newton, sigma F equal to m times a. And then the second method is by using energy, which is T plus V1 equal to T2 plus V2. Energy, and the last one is by using the momentum, either the linear momentum or angular momentum. You remember that? Angular and linear momentum. Right, so in this case, in the last topic of ours about dynamic forces of mechanisms, we will analyze the force only by using the second law of Newton. Second law of Newton and Euler moment. Okay, I will erase this. Because you have known from the previous topics based on the rigid body. So basically dynamic force of mechanisms is quite simple, because you divide the four-bar linkage becoming several rigid bodies. So in the dynamic force analysis of mechanisms today, the method that I'm going to use is second law of Newton, sigma F equal to m times A, and this is Newton, Sir Isaac Newton. He just got his birthday last month. I saw it in Instagram that he got his birthday last month on December. And then the next method, no, we are using the first method, second law of Newton, and also Euler moment, which is sigma moment equal to I times alpha. This is, we call it Euler moment. Because Newton, he proposed only for linear motion. So this combination, we call it Newton-Euler method. Okay, now let's take a look. If you remember our second quiz, you have a pendulum like this. We'll try it here with black. Inverted pendulum, probably. So if you remember, you have this pendulum like this. So this is considered as a single rigid body. You remember this, and find the reaction force at point A, for example. Find the reaction force at point A. So it means, you know that because this is two-dimensional space in X and Y. So if I put the coordinate system here, this is X, this is Y. So it means we have two components of, for example, Rx, Ra at point A in the X directions. And this is just an assumption, Ray. Okay, and what else we have here? So before writing the equations, you have to decompose by using the free body diagram. So we call this as a free body diagram. What else we've got here? We've got here, there is the weight. Okay, and because this is not constant, because the velocity is not constant, so it means it has accelerations. So v is not constant, it's not null, neither zero nor constant. So we have A. V is not constant, so we have A. Okay, then we have also, because it is rotating, we have theta and we have theta dot. Okay, we have theta dot, and then we have theta double dot. It depends. We can have dot or not, depends. If theta dot is constant, so that theta double dot will be zero. So you have the weight, then what else you have? You F. So basically we have two components, tangential force Ft, and we have a normal force Fn. Okay, that's it. You can also define the free body diagram this way. So we have this. Okay, so you can also describe the free body diagram. Here we have, of course, we have a reaction force, Ry, and then we have a horizontal force, the reaction force in the x directions. And you can also describe it here, W, the weight is going downward. And you can also describe it as a F inertia in the x direction and F inertia in the y directions. So both free body diagram above and at the bottom, both are valid. Both are okay. Then from here, you define the equations of Newton. Sigma F equal to m times a. Okay. Now, if you isolate only the rigid body, you can erase the joint, right? So now if I isolate, now my question is the joint a rigid body? No, it's just a point. So we can erase this. So now we isolate this rigid body. Okay, we isolate this rigid body. If you remember, here we can replace joint A, only a single point here as a A. Then we can draw the reaction force Rx and Ry like this. So sigma F is equal to m times A. The question is, what is A here? A is a linear acceleration of point, which point? This point, okay? The center of gravity. Let's call this point G. So A is acceleration at point G. So A here is at point G. And what is sigma F? Sigma F is all the external forces. So what is external forces? External forces is the reaction force, depends. Do you have, here again, we can write it as a vector form. That would be simpler. So if I write it as a vector form, now let's say you can get acceleration of A at G based on the kinematics. If you remember the kinematics of mechanisms, you should find the accelerations. Let's say find the acceleration of G like this. So you can find it in the form of x and y. So here ax and ay. Okay, and then now you can put it here immediately. So sigma F is a vector, A is a vector, M is not a vector. So here I can simply say that here is I have Rx and Ry, okay, and then plus, what do I have here? I have W is going downward. So does W have X component? It doesn't have, so we can put it 0. And here we can put it M times minus G. Why minus? Because it is pointing downward while our coordinate system Y here, the red color here, is pointing upward. So the direction of the weight is against the direction of the coordinate system. So I will put it here again. Here is our X coordinate system and here is our Y coordinate system. Okay, and I will go back to the equation here. So I will put here m times minus g equal to m, the same m as here, m times ax and ay, like this. So this is the sigma F for this. And also, you should also derive the equation of Euler moment. So sigma moment is equal to I times alpha. So sigma moment here, because this is two-dimensional space, so sigma moment, it occurs only in the z directions. But sigma moment, you should always write it down here with respect to which point. Is it with respect to G point or with respect to A point? It is up to you. Okay, so if you, let's say it depends on the questions. Let's say the question is find the reaction force at point A. So it means you should find the Rx and Ry both. So if you want to find both, it means I don't want to know about Fy, Fx. So I will just simply type it here, sigma moment at point G. So what is alpha here? Alpha here is the rotation of this rigid body. Okay. I believe you still remember here because here is exactly at point G, so we don't have Fx and Fy to be included in the equations. And I, you can type it I here because the center of rotation is at point A. If you remember, so you can type it directly I at point A. Okay, or you can replace it by using I times G times alpha, okay, then plus Fy times the length. So basically, you can also, this is simple if you just type it F tangential times the length. Let's say the length is L, the full length is L. So I will type it L times 2. Okay, this is a review from dynamic analysis of rigid body. I believe you all remember this. I will erase this now. We'll come to the mechanisms. Now we come to the mechanisms. How about if we have arrangement, not an arrangement, if we have an assemblage, this is, we call it assemblage, because we have an assemble of several rigid body become one single Fobal linkage. You see, here we have a link, here we have a link, and here we have another link. Okay, then let's say the input torque, this is the input, this is the crank, so this is the input. Let's say here I put a motor so that it produces some input torque, okay, Ti. Right, now let's say here I want to measure it. So here I want to measure it. I want to know what is the torque resulted, what is the T out. from the input torque from the motor. This is the motor, DC or AC, it's up to you. Then it gives some input torque for example, 10 Newton meter. So what is the output torque here produced in this point, in this link, let's say. So now, how are you going to solve this? So the way we are solving this, we have to divide this into 3 rigid bodies separately. Okay, let's call this rigid body 1, rigid body 2, and then here rigid body 3. And again, we can call this point A, here is point B, here is point C, and here is point D, right? And we place a coordinate system here at point A, X and Y, which is here. And now draw the free body diagram separately one by one. That's what you have to do in the first place. Okay, in the first place, you have to draw the free body diagram for body 1. So for link 1, we draw it simply like this. Then we can call this point A. Here is point B. Then free body diagram for link 2 is like this. This is link B and this is link C. And free body diagram for link 3 is the crank, the output. This is point C and point D. And then now, is it enough? This is not enough. You have to draw all the necessary forces. If you take a look at the left picture, we have a 4-bar linkage. So each point it has joint. So it means each point it has reaction force. Okay, so here we have reaction force to the x direction, R A X, and then R A Y. Okay, then here at point B, because this is also attached to a joint, so we can write it like this, R B X and R B Y. For free body diagram link 2, we have also point B. What about the reaction force? Here is what you have to remember, because B for body 2 and B for link 1, they are the same. So the value, okay, the value RBX here should be the same as the value RBX for link 1. But the direction, they should be opposite. They should be different. So RBX. If RBX is going to the right, so for body 2, RBX is going to the left. Okay, the same here is going upward like this, RBY. Okay, but remember the value here, they should be the same as here. The value, I'm talking about the value, they should be equal. Right, how about point C? Point C, it has also reaction force. Let's assume in this direction, RCX, and in this direction, RCY. Here also reaction force at point C here and at point C from the body to the value should be the same, okay? But the direction should be the opposite, RCX, and here it is, RCY. Now here at point D, this is also attached to a joint. So we'll have a reaction force RD, not sure, RDY and RDX. Okay, is it enough? Is it all? This is not all. We have what else we forgot here? We have the torque input, the input torque which is here. So you should write here, T in, torque input. That's it. Once more, you remember that each link, it has G. So we can call this G1. Here is G2. And here is G3. Okay, so it means at each G1 to 3, they have their corresponding inertia force and moment. Okay, so it means we have to draw the moment. Okay, and we should also draw the force at center of gravity G. So I will draw the tangential force and also the normal force. This is a lot simpler. And here also the same. You can put it the tangential force like this and the normal force either to the B or to the C. Both are okay, both are fine. Okay, this is Fn, and we have also a moment. And here is also the same, we have a moment, and we have a tangential force, Ft, and we have also a normal force. Is there any questions so far?
Hello, Miss.
Yes.
I want to ask about the direction of RIY and RIX.
RAY and RAX, yes. What happened?
Is it correct, ma'am? RIX to go upward.
At this point, yeah, that's a good question. Thank you. So at this point, we don't know yet because from the computations, if you remember, if you compute by using the sigma f equal to m times a, which you remember in the rigid body analysis, somehow you will end up at RAX equal to minus 30 Newton. So here you should give a note, this is in the opposite direction from the FPD. So it means it is, oh, you mean the notation. Okay, sorry, the notation.
Yes.
Okay, thank you. Yeah, the notation is wrong. But here I'm talking about whether is this direction correct? At this level, we don't know yet because we are not coming to the computation yet. So we can make an assumption that it is going upward. It's okay also if you make an assumption that it is going downward. Okay, both are correct. So once your calculations say this is minus, so it means your RAX is in the opposite. And you can give a note like this, opposite from the free body diagram. Okay, thank you for the questions. Is there any other questions? Just shoot it, just talk directly. So now, yeah.
I want to ask If uh, if if we apa if in the question doesn't state the mass of the links, so we can ignore the gravitational force, ma'am.
Okay, so thank you. So the mass for each link will be given. Otherwise, you cannot calculate the sigma F equal to m times F. So m times A, sorry. Here you will need mass. And sigma m I times alpha. Finding this, you will also need m, like 1/3 m times L square, and etc. So what I will not state in the questions is if I said that gravitational force is neglected, then you can neglect it. But as long as I don't say gravitational force is not neglected, so you should also compute the W going downward. Okay, so mass of each link is a mass. It will be mentioned in the questions. But what I will not mention is probably the gravity. But if I mention, let's assume that gravitational effect is too small so that it can be neglected.
All right, ma'am. Thank you.
You're welcome. Is there any other questions? Okay, I will continue from here. So we'll finish today with a 4-bar linkage, and next meeting we'll continue with slider crank. There are many types of slider crank. There is also this type of slider crank. For example, like this. We'll discuss it next meeting. So find the reaction force here instead of here, and so on. Okay, now the question is, what is the output torque? What is the output torque of at point D for link in the link C? So here I have to draw the output torque. I forgot here. Here it has output torque, T out. This is quite simple, basically the same as the rigid body. The difference is only you have to type sigma equal to A 3 times. So each for the corresponding link 1, 2, and 3. So you can say AG1 sigma F equal to MAG2 and sigma F equal to MAG3. Are these enough? No, you will need also sigma M. At which point? All right, now for link 1, let's type it here, link 1. For link 1, sigma M will be with respect to which point? Again, this is up to you, because remember, for one link like this, how many unknown? Let's talk about unknowns. Okay, let's talk about unknowns. How many unknowns for link 1? So here I have unknowns. We have RAX, RAY, RBX, RBX, and RBY. Okay. We also have FT and FN. You can also write it as FX, FY. or we can write it as a ft, fn. That's it, right? Yes. And here in this link to how many unknowns we have, rbx, rcx, we have rbx, rby, rcx, rcy, and we have the inertia force, ft or fn. And in the last here we have rcx, rcy, rdx, rdy, and we have T output. Okay, so actually the inertia force here is not really considered, because this is inertia. This is in the inner forces of each link. So unknown is basically the out or the external forces. Yes, the external forces for the links. So we have here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 unknowns. So we have, what is the 9 unknowns? We have RA, this is 4. So B between here and here are the same. So we can consider here 6. C already consider. So we have 8. And then the last one we have T out. So we have 9 unknowns overall. Okay, so it means you need about, if you want to solve everything, let's say find all the value of reaction force. Find all reaction force. So you have 8 reaction force, and find also T out, the output torque. So overall you have 9 unknowns. So it means you need 9 equations. Okay, but the question is only find the output torque. So you will still need 9 equations, because you should going from here. Let's go to the let's go to the drawing, the above drawing, because the way you are going to solve is from this coming to this and then finally here. So it means 1 by 1 for each link you will need equations. So you still need 9 equations, but you don't have to solve all values in the equations. Okay, let's try to solve first for link 1. Okay, for link 1, you have sigma F equal to M times A at point G1. Okay, what is F here? F, we have the external forces. What and all the external force? The red color are external force in the free body diagram here. We have RAX, we have RB, RAX, RAY. We have the input torque, we have the RBX and RBY. Okay, you can either type it as a vector, or you can type it 1 by 1 as a X and Y. For this case, I will let you to decide. So if you want to type it as a vector, that would be easy, because here I will erase it here. Let's try by using vector. One and all the axial force, we have RA as a vector, plus RB is a vector, and then plus, do we have any other axial force? No. So that's it. Equal to M times A G1. So if I type it as a vector, I will put it like this: RAX, RAY, plus RBX and RBY. M times A in the X direction and A in the Y direction for point G. Okay, so from here, actually we have already two equations. Equations for X and equation for Y. So you can also type it as a scalar, it's okay. So sigma F in the X direction, this is the same, M, but you should type it AG1X so that I understand that this is in the X direction. And then sigma F y equal to M times AG1Y. Okay, we have two equations already for link 1. Do we need another equation? Yes, we need one last equation, which is sigma moment. With respect to which point, it is up to us. Let's say with respect to G1, I think I made a mistake. Did I make a mistake before? Okay, so if, let's say if this is with respect to G1, so here we have M, sorry, I times alpha. Okay, is there any questions? All right, please remind me again if I'm afraid that I was mistaken before. So if we consider that sigma moment at point G, what is the I here? Is it I at point G or I at point A? Is there anyone who can give me a hint or suggestion? Okay, I will take a look later on. So now for link 2, you will do the same. So for link 2, you will have 3 equations as well. And then for link 3, you also have 3 equations. You see, now you have, overall, you have 9 equations for 3 links, which means you can solve what is the value of T, the output torque. Here, from the equation of link 3, you can find the output torque. All right, is there any questions?
Excuse me, Miss.
Yes.
I want to ask in the calculation why there's no weight the
Yeah.
W in the calculation of the sigma f.
Yeah. What is your question?
Why there's no W there in the calculation?
Oh yeah.
Mass times the gravity.
Okay, so you're right. So we have a W. I missed it. W. So we put it here plus W vector. W vector. So it means here we need M times G. Plus, so where should we put plus minus if we are writing it as a vector? So you can put it inside this. For example, Rx is going to the left, so you can put it as minus here, or you can put it here as a plus minus. You can put it inside the bracket. The same as here, I will put it 0. Then because going upward is positive, so I will put it m times minus g equal to m times a in the x direction and a times in the y direction. Okay, thank you. Is there any other questions? I have so I have finished with the FOBA linkage for today. We'll continue with slider crank mechanisms for Thursday. Do I have I will check if I have an exercise. So if I gave you exercise, you should try it by yourself, because in the class usually what I do is to show you how to solve it, but I am not going to solve it myself, so that you will learn from what I have given you. You will apply it and try it at home. Okay, let me check if I have oh no, it's not here. Let's try if I have something from before. Okay, so unfortunately I didn't have questions. I don't have exercises here. I will give you on Thursday, but I can find something for you so that we can try it at home. Wait a minute. Okay, so I cannot find it. I'm sorry. Let's meet again on Thursday. I will finish with slider crank mechanisms, the dynamic force analysis. From the previous computations, I hope that you can finish it. So from here, I have written it for you for link 1. So I hope you can finish it for link 2 and link 3. I will not force you to do it because this is really will benefit you if you want to do it by yourself, because I have done it long time ago as a student, and now I'm still doing it as a teacher. So now it's your turn to derive the equation for link 2 and link 3 until you can find the output torque. I will give some value here so you can try it at home. Let's say that the input torque is 10 Newton meter, and it has a theta. It has a theta dot. It's some value. It has a theta dot. Let's say 5 radian per second, and all the masses are the same. Mass 2 equal to mass 3. Then find what is the output torque resulted here for the output link. All right, that's all for today. If you don't have any other questions, try to derive the equations for link 2 and link 3. And I will give an example for Thursday. Then we'll continue with the slider crank mechanism. For slider crank mechanisms, I would say it's a lot simpler because the reaction force for slider is only one. Okay, for a pin joint like this, the reaction, you will have two reaction force in the X and Y, but for slider, it has only a vertical reaction force. Okay, that's it for today. Let's meet again on Thursday. We'll continue with some examples, some exercises, and once again, try to do it at home. As I told you, I have done it myself as a student like you. Now I'm still doing it as a teacher. Now it's your turn to do it. And we'll have the last quiz, the fourth quiz on Monday. I hope Monday is not a holiday because next week is the week for final exams. Yes. So Monday, 11th January, we will have our fourth quiz. As soon as possible, I will announce the marks. Then we'll do the remedial test at the latest Friday. I hope Thursday, but at the latest is Friday. All right, thank you for coming and see you on Thursday.